Okay, for the convex mirrors, the object is placed in front of the mirror, and the focal point and the center of the mirror are at the back of the mirror. That's why there is only one location for the object in front of the mirror. It is between the mirror and the infinity. So, how can we locate the image for an object in front of a convex mirror? Let's draw several light rays from this point and see where they are going to intersect. A parallel light ray to the convex mirror will reflect such that its extension will pass through the focal point. Another light ray from this point to the center of the convex mirror will reflect back. This light ray is moving toward the center of the mirror, but it strikes the mirror and reflect back, so its extension is again going to go to the center. One more light ray from this point to the focal point of the mirror. It is directed toward the focal point of the mirror. It will reflect parallel to the principal axis. So this is the first reflection, this is the second, this is the third reflection, and this is the second reflection. I mean, I have three light rays coming from this point of the object, and they are all reflecting. So while they are reflecting, their extension, the extensions of the reflected rays, this one, and that one, the extension of the reflected ray, in this case it is reflecting like this, its extension is this one. So they cross at this point. The image is going to be formed somewhere here. As you see, the image is erect, it's not inverted. It is smaller than the object. It is between the focal point and the mirror. What if we take this object to the infinity? Or what if we move this object toward the mirror? When you take the object to the infinity, this image will get smaller and smaller, and it will be a point at the focal point when the object is at the infinity. But when you move the object toward the mirror, this image will get bigger and bigger at the when the object comes to the comes near to the mirror. The image is also going to move toward the mirror, and they are going to meet at the mirror, and they are going to be equal size. It is better to show it with an animation. Let's go to an animation about the image formation in concave and convex mirrors. Assume we have an object somewhere here, and this is a convex mirror. This back side is reflective. It reflects the light rays. When the object is here, this is the image location. Let me move backward this image, and I'm going to move this one toward the infinity. And do you remember I told you that when I move the object toward the infinity, this image will get smaller and smaller. It will go to the focal point and then becomes a point. Let's see what will happen to the image when I move this object to the infinity. As you see, when this is moving to the infinity, this image becomes smaller and smaller it becomes, and at the focal point it will be a point. So what if I move the object toward the mirror? See, the image is getting bigger and bigger, and as you see at the mirror point they meet and they become the equal size. Okay, what about the image formation in the concave mirror? Okay, in this case here is the object and this is our concave mirror. This side, the invert, this inner side is reflective. Our object, let's say, is somewhere here behind the center. As you see, when the object is behind the center, the image is between center and the focal point. When I move this object toward the center, as you see, the image is getting bigger and bigger, and then it approaches to the center. As the object approaches to the center, at the center they are equal size and the image is inverted and it is a real image. Its properties are written here. Height of the image is smaller than height of the object. Why? Because they are not exactly it is difficult to locate the position of the image and the object. Actually at the center point they are equal to each other. Okay, what if I move the object toward the focal point? As you see, as I move the object toward the focal point, the image is getting bigger and bigger and it moves to the infinity. When I come to the focal point, as you see, these light rays reflecting from the mirror are going to the infinity. At the focal point the image is at the infinity. When I pass the focal point and approach the mirror a little bit, as you see, the reflected or light rays are diverging. They are moving away from each other, but their extensions are crossing somewhere here. So the extensions of these reflected light rays is composing a new image, and this is a virtual image. Why? Because the not real real light rays are crossing, but their extensions are crossing. In this case, this is a virtual image. As you see, the image is bigger than the object. What will happen if I move the object toward the mirror? So this is also going to move toward the mirror, and it will get smaller and smaller. At the mirror they are going to have equal size. Okay, let's move back to our sheet. Okay, so the summary is here for different object positions, the image position. For example, let's look at the second one. When the object in the concave mirrors, when the object is behind the center, the image will be between focal and center. The size will be diminished. It will be smaller. It will be a real image and inverted image. Let's go to our image formation in concave mirror when the object is between the focal point. No, I'm sorry. When the object is behind the center. Yeah. Here, as you see, as the object is behind the center, image is formed between center and the focal point, it is inverted, and it is smaller than the object, it is diminished, and it's a real object. We can also check it with the simulation here. When the object is behind the center somewhere here, when here is the center of the curvature and the object is here, image is formed between center and the focal point, and it's inverted. So similarly, you can check this table. I'm not going to go into the details of this table. You don't need to memorize this table. Just this is a summary. My recommendation to you: use ray diagrams to locate the image position and find the properties of the image. Let's move to solve some problems related to the image formation. Now we have an object. It is like a square. This is our object. So how will be the image of this object? Now, so far we looked at only this type of objects. Now here we have a box, for example. In this case, how can we draw the image of this object? As you see, this is a rectangle. Assume here we have an object. Assume this is an object. And assume this is another object. Assume we have two different objects. Let's find the location and the size of this object and that of this object, and then we are going to connect them to find the shape of the image. As you see, when the object is at the center, remember, when the object is at the center, image is inverted and equal size. So the image of this object will be equal size and inverted. What about the image of this object? This object is between focal point and the center. So when the object is between the focal point, here is the focal point and here is the center, the image is between the center and the focal point, the object is between this focal point and the center, the image is behind the center, and it is bigger than the object, and it is inverted. So when the object is here, we are going to get an image behind the center, inverted, and bigger than the object. So when I connect these 2 points, I'm going to get the shape of the image of this object. It is going to be something like this. Okay. This was an image formation in concave mirror. Let's look at one of them in the convex mirror. Similarly, assume we have one object here and another object is here. For the convex mirrors, in front of the convex mirror, we don't have focal point, we don't have the center. That's why let's look at if this object is closer to the mirror or away from the mirror when compared to this one. As you see, this one is a little bit further than the mirror when compared to this one. So as object approaches to the mirror, as the object approaches to the mirror, its size increases. Let's go to our simulation for the convex mirror. Okay, assume our object is here. Now assume here is the rectangle. at point 4, point 8, and this is assume our rectangle in our question. Okay, so what is the image of this object? It is 2 centimeters approximately away from the mirror. So if I move, what is the image? Where is the image if the object is somewhere here? As you see, when you move away from the mirror, when we move away from the mirror, the image moved toward the focal point, and it is now a little bit smaller. Okay, so let's assume that the image for this object is somewhere here, smaller than the object. Why? Because image is always smaller than the object. When you move backward, the image becomes smaller and approaches to the focal point. So if I connect these two, this is going to be my image. Okay, let's move to the next question. Two candles of equal size are in front of convex and concave mirrors. What is the relationship between the images and image distances? Okay, so what is the relationship between the images and image distances? When an object is in front of a convex mirror, the image is formed between the mirror and the focal point, and it is smaller than the object, and it's a virtual image. But when an object is at the center of a concave mirror, this is a concave mirror, and the image is going to be formed at the same size and at the same location and inverted. Initially, X and Y candles have equal size, but their images will not have equal sizes. First of all, the image in the concave mirror will be bigger than the image in the convex mirror. And the image distances, this image is closer to the mirror, and this one is a little bit further to the mirror when compared to this one. That's it. Let's look at the next question. Two pencils are moving toward the convex and concave mirrors. How will the images in both mirrors change? Do you remember in our simulation, when the object is moving toward the convex mirror, the image gets bigger and bigger. When both come to the mirror, the both image and object will be the same size. So when this is approaching to the convex mirror, the image will get bigger and bigger. On the other hand, when this object is moving away from the concave mirror, it is initially at the center. So remember, by the way, 2f is equal to the center. That's why this is the center. The focal point is somewhere here. So when the object is at the center, the image is at the center. When you move beyond the center, the image will get smaller and smaller. It will get smaller and smaller as you move toward the infinity. At the focal point, when you move this object to the infinity, the object will come to the the image is going to come to the focal point, and it's going to be a point. So the image for this one is getting bigger and bigger, the image for this one is getting smaller and smaller. Okay, let's look at the image of this shape. As you see, this is an interesting shape. This is a T-shape object. Where will be the, how will be the image of this object? Now assume that we have an object here. Okay. The objects in front of the convex mirrors are virtual, and they are formed at the behind of the convex mirror, and it will be smaller than the mirror, smaller than the object, sorry. So this is going to be our image of this point, image of this line. What about the image of this point? First of all, assume here we have an object. Let's say this is our object. And assume we have another object here. Remember, as you approach to the mirror, the image gets bigger and bigger. So the image of this point will be higher than the image of this point. The image for this point will be somewhere here. And the image of this point, this is a little bit away from the mirror, is going to be somewhere here. So when you connect these 2 points, you are going to get the shape of this T-shaped object. So A will be here and B will be here. Okay. Then next we are going to solve some problems for the spherical mirrors.